Today we're building this awesome SpikeField animation using Raylib and C. This will mostly be shader-based implementation. Raylib helps us to create a window and load different assets like image and shaders. The inspiration for this project was an image I found quite long time ago, but I saved it and it kind of made me want to reproduce it in a way that we get not only a static image but a running animation. So by the end of this video, hopefully we'll be able to have this thing running, and yeah, I guess we can get started. So first things first, we create our repository for this project. We call it SpikeField. We'll use C, git ignore, create our repository, and once it's created we can clone it, jump into it, and see we have nothing in it. We can now bring our CMake template, which is configured to use C23. We'll call our app Pi. We have this LSP support, some compilation flags to make it strict. We simply compile everything in our src folder. Raylib is already pre-installed, so we want it to be found by CMake and then linked during the build time. Let's create our src folder, touch src main, jump into our main and quickly check that our Raylib setup works fine. So this will be a very small and tiny window setup. We can say init window with some params, something like this. We'll give it a title SpikeField, target FPS 60, then window should close, not until we need to close, we do something, in the end we close the window, and in our while loop we can say begin drawing, end drawing, and in between we can draw some text. Let's say SpikeField, position 100, font size 100, color red, and we can clear background, something like white. Right, so this is a skeleton of our app, our starting point. This just makes sure that our setup works. So let's set up our alias. CM stands for CMake be built and build, and another alias which not only builds the project but runs it, build Pi, and we call it CMX. Right, so if I run CMX, then we get this nice Raylib window. We made sure that it works. Alright, so first thing that I want to do is I want to draw a background. It's going to be a little bit animated and it will introduce a few things that we're going to be using during our SpikeField development. So let's start with creating background H and background C. We jump into header file, define pragma once, and here we will expose type background without exposing the internals of our structure, which is going to be defined in C file. Then we will define a few methods that will allow us to work with the background. I'll use a Raylib type notation, not like C1, so bear with me. First of all, we need to load background. Then we need to be able to draw background. And finally, we need to be able to unload background. So release everything that we allocated somewhere during the background setup. Now that we have this, we can copy these methods, jump into our C file. We'll definitely need the Raylib here, and we can include our background header file, paste the methods signatures, and let's see. First of all, loading a background. We can say that background, we use Raylib's allocation capabilities, size of our background struct, which is typed as background. We need now to introduce our struct background. And what we're going to do is we're going to be pretty much relying on a shader to draw everything. We can return our background, and the only thing that we need to set up currently is shader, load some shader. It doesn't need any vertex shader, so we can say it's going to be null. And for the fragment shader, we say assets, shaders, background fs. For unload, we can instantly say that, hey, how about we unload shader? Maybe, I don't know, like whether it's really needed or not. But what we need to do is we need to mem-free our background. As for drawing the background, what we want to do is we want to say, I think, begin shader mode, so that our shader is applied during sequential or the following drawing commands, and end shader mode. And in between, we want to draw a rectangle, pretty much spawning the whole window area. So it starts at 0, 0, and it uses the whole get window, I think, width. Wait, no, what was it? Get screen width. And here it's get screen height, and color will be something like black. All right, so this is like basic setup. We don't have any shader setup yet, but we can already. Okay, let me just quickly create git ignore, and not create, it's already there. We need to put build here so that it doesn't include the files in my file search. So if we jump into main, we can now include our background header and start using the methods that we just introduced. So we load our background first, which loads the shader eventually, like not right away. Then once we have drawn the text, we can say draw background please with our background, and at the end we can say unload background please. Now if we run it, what we see is black window. Raylib tells us that it failed to open text file, so I don't know like whether it used some default shader or just ignored shader at all. But what we have done is we have overwritten whatever was there before, so our draw rectangle drew everything correctly. Now we want to actually start using the shader so that the vertices of our draw rectangle end up in our shader, and we can work with colors, introduce some coloring to this background. So first of all, we need to create folder assets. Inside of it, we need to create folder shaders, and here we create background fs, which stands for fragment shader. Now I need to first say that this is GLSL. For some reason it detects it as different file type, version 330, and we're saying that the result of this fragment shader is going to be vec4 frag color, and we can instantly define it here, saying that color with alpha 1, where color is something like let's say red, so RGB, R is 1, G is 0, B is 0, ends up red. And if we run it right now, we see that our shader now loads just fine, and for every single pixel, so to speak, right, fragment inside this rectangle, we apply our shader, which returns red color. Let's name it red. Then we can introduce another color, let's say green, which is like 0, 1, 0. And now I want to mix those colors. I want to introduce a gradient so that from top to bottom we go from green to red, and we can do that using linear interpolation, which is called mix in GLSL. So from red to green, vec3 color, and here we need the row that we're working with, so the y coordinate. By default we have frag coord, which says that this is actually a window relative coordinate, so it depends on our window size, render area where we are working with. So these values are from 0 up to window width, which is x, and y is like from 0 up to window or render area height. But we would like to normalize it into something like 0, 1 range. Usually that thing is called UV, and if we have our coordinates of the fragment, then if we grab resolution, right, if we grab only XY, because this is actually X, Y, Z, and W, this is vec4. If we grab vec2 of our XY coordinates of this particular fragment, or we can think of pixel, and then divide resolution, then resolution also has XY. So X will be divided by the whole resolution width, Y will be divided by resolution height. Thus, we'll have UV, where both X and Y values lie in range 0 to 1. And then we can say that based on the Y or row value, you can grab the color, linearly interpolating it in between. So if Y is 0, in this case, this is the bottom of our window, that's where Y starts at 0, we will pick red. At the top of the window, where Y is 1, we pick green, and in between, as Y grows, we go from red to green. Unfortunately, this resolution is not available to us, so we need to somehow supply it from the outside. That's where we're going to use our first uniform, vec2 resolution, and we're going to supply it from our background C. Now that we have this uniform in our shader, we need to actually grab its location. So resolution location, we can say that its location is get shader location with our background shader. So this is specifically get shader uniform location with given name. So this name resolution must match the one in our shader code. And then we need to somehow set it, right? And ideally we should set it on every single frame, because window size might change if we want to Therefore, we would need to introduce yet another method. Let's say update background, which will accept our background and some width and height. And let's say it will set shader value given our shader. Location index is the thing that we just retrieved, resolution location. The value is going to be resolution, and uniform type we need to provide uniform. It is going to be vec2, right? So vec2 is vec2 floats. Now our resolution is going to be implicitly converted to floats from width and height. Right, so now we need to open our header file, add this method signature here, jump to our main, and on every single frame we're gonna invoke update background, our background width and height, where, well, I don't think that we need to extract that. We can say get render width and get render height. So this thing actually can be different from get screen width and get screen height, because it considers high DPI displays like Retina on MacBooks, like I do have. So if you put screen width, it might actually work for you depending on which screen you use, or it might actually not work. So it will draw things differently than what you see here in this video. All right, so have we done everything? If we have done everything correctly, then as I said, this is the screen that we were trying to achieve. Our Y is 0 at the bottom of the screen. That's why it's fully red. Our Y is 1 at the top, and in between it starts interpolating the color. This static color is of course nice, but we would like to animate it. And for animating things, we usually need a notion of time. That's where our second uniform comes in, float time. We need to do the same thing as we did before. We need to introduce time location in our background struct. We need to grab it from the shader time, and we need to of course update it every single frame. So we need to pass the time to our update background function and set the shader value at time location time, and this is going to be not vec2 but float. Jump to header file, update the signature because we now have this float time here, and jump to main because this thing now wants time as well. What is time? Well, it's a simple variable. Float time starts at 0, and every frame we simply add get frame time, which is delta time, right? Frame drawn delta time. How much time passed since last frame. So this accumulates time in our time variable. It gets updated on every single frame and ends up in our fragment shader, which can now use it. So before we start using it, I would like to show a few things on Graphtoy. These are some interesting things, but we need, first of all, like sine of x, right? You must be familiar with that. So starts at 0, goes up to 1, then how do I move it? Yeah, then goes down to -1 and back to 0, right? This is actually 2 pi, so 628 something. Now there is also this Graphtoy has something like time, so we can, I think, t, right, sine t, so t always grows, and as you can see, sine t just goes for every single x value, always produces the same output. Now, when we're dealing with the wave, currently it's a sine wave, we can adjust it, right, by saying that I would like to have it more frequent. That's where we add some frequency. So for example, I want to do the one full like full interval of sine, not in 2 pi, but in 1 pi. So it should end up at 314. So our frequency, we can say, hey, please do it twice faster. So now it ends up right here at 314. We can do it times 3, or we can do it slower, twice slower, for example. So this is our frequency. We can make the sine wave more frequent. Next, we can also apply some offset. So right now it starts at 0. We can say, hey, please, let's start at 0.3, or in other direction, minus 0.3. Finally, we can also apply amplitude, or not apply, but configure the amplitude. So right now it goes from -1 to 1, and if we multiply outside of sine, let's say by, I don't know, 2, right? The amplitude becomes -2 up to 2, or like 0.3, which makes our sine wave go from -0.3 to 0.3. So this is this thing that we're going to be using in both background shader and later on in our SpikeField shader. So let's see. Let's define our wave as sine over time. Right, so time we're passing as uniform. Sine gives us values from -1 to 1, and instead of having for each row its own color, let's say that we will have color for all the pixels. It will always be the same, but as time changes, so does the color changes. Now, as you can see, the timing of these color changes is unclear. Sine works with radians and time is seconds. So somehow we want to tell how this time correlates to radians, and we can say that let's let the sine do one full interval, so from 0 go up to 1, go down to -1 and back to 0 in 1 second. And because that happens in 2 pi radians, right, so we can do something like this. Now this 2 pi is actually called tau. If we search for tau constant, here it is, and we can just, I don't know, copy its value, define it as a const float tau. So now if I start the same window, it is blinking from red to green in 1 second. So the whole interval, red to green, red to green, red to green, happens in 1 second. Now, one thing to note is that red is shown for a greater amount of time than green. Why does that happen? That happens because sine actually returns values from -1 to 1, meaning that half of its values, which are negative in the mix, end up always as being red. So anything that's below 0 is considered to be 0, so it ends up to be red value. That's why red is shown twice as long as green. We can of course fix that by first applying different amplitude, which makes it from -0.5 up to 0.5, right, and adjust it by adding 0.5, which makes it interval from 0 up to 1. And in this case, both red and green should be shown with the same amount of time dedicated to them. Now, as I said, we can do it less frequent, for example, 2 seconds for a full interval, or we can make it twice as fast. So it takes half a second to do the full blink from red to green, back to red. And what else? If we make it a bit slower, as you can see, it starts from green, goes to red. We can apply our offset, or phase it's called, where I can say, let's do tau divided by 2, meaning we want to shift it by half. So instead of starting at green, it should start at red, right? So it starts at red, goes to green. So everything that we have seen on Graphtoy applies here. All right, so now what can we do with it? What we can do with it is we can define things to be more understandable for those who are going to read the code. So first of all, like frequency is going to be 0.2, so we make it quite slow. Full sine interval in 5 seconds. Then phase or offset, we can do tau divided by 2, right? So shift sine by half, pretty much make it cosine. And then we can also change its amplitude, right? We call it amplitude by half. So this now ends up in a range of minus 0.5 up to 0.5. And next we can actually say that, hey, let's do our row plus the wave. Let's see what that does. Now this gradient thingy is actually moving up and down, but I don't know like whether the video captures it. There is a artifact at the place where the I think 0 is, or 1 right at the top. So why does it move the way it does? So y is always from 0 up to 1, and wave actually adjusts it, right? So imagine wave is minus half and y is 0. So it actually picks red, and then it picks red for half of the screen up until y is 0.5. And then it starts moving linearly towards the green. So that's why we see most of the screen being red. Now this doesn't look good. As I said, there is some artifact and we want to fix that. And let's start fixing it this way. First of all, we'll use step function, which tells you that if the value is less than 0.5, it's going to be 0. If it's more than 0.5, it will return 1. So really, step can only return 0 or 1. And we have a value to compare to, and the value or variable producing the value itself. This is where we say uv plus wave. And now we can use this t instead. So it will show either 0 or 1 depending on the row we're at, and the wave also applies to it. Now we get an interesting effect where it goes from green to red and back and forth. Again, you can actually try and think how this is achieved or why it works this way. So for every row on the screen, it is adjusted by the wave value. So for example, if wave is 0, right, so it doesn't affect anything, so half of the screen below, or lower half of the screen is going to be red because it's less than 0.5, so t ends up 0, and in our linear interpolation it will simply pick red, and in other half t becomes 1 and we pick green. But let's say as wave grows, as it's positive into positive side, 0.1, 0.2, it means that lower y values, so for example 0.4, ends up being, well, summed up with wave, ends up being larger than 0.5, and t ends up being 1. So in this case we get more green on the screen, and when wave starts decreasing we have more and more red. Now one thing we can do is introduce smooth step. Now if I put the values like this in our smooth step, right, I don't think this one very useful, but yeah, it's like smooth interpolation between the edges. So everything lower than this edge is 0, everything greater than this edge is 1, but the values in between are actually interpolated from this edge to this edge. In this case, when both edges are the same, it acts absolutely the same as the step function itself, so nothing really changes. But if we say that all the values less than 0.4 end up being 0, all the values greater than 0.6 end up being 1, and in between it gets linearly interpolated, then we'll see this gradient in this particular like white line. Next we can of course increase it and see what it does. So the gradient increases, and finally, like final thing that we're gonna do is probably something like this, right? So we make it almost disappear, so just has some nice visual effect. The most important part in this shader was actually introduction of these waves, frequency, phases, amplitudes, and just to make it a bit nicer for the final result, I'm gonna redo the colors. Instead of using red and green, I'm gonna use some purple colors. Let me see, so just going to be some dark purple, which is going to be something like this, and then there's going to be some deep dark purple. And I think something like this. So if we run it, right, actually once we made the changes, our app crashed because the fragment shader code failed to compile, and that's because I renamed the variables, but I'm still using red and green in my mix function. So I need to say deep dark purple and dark purple right here. Now if I run it, we can see the changes in the purples. Again, like due to video encoding, I don't see whether it's visible or not. Let me do a quick change, like for example here, make it a bit lighter. So yeah, I think this should be noticeable on the video itself, right? You can see very dark purple and this one quite light purple, but I will keep it as it was. Hopefully it's distinguishable. All right, so this is it about the background, and now comes the more interesting part, is our SpikeField, where we show the Pi symbol. All right, so we need to do what? We need to do the same thing as we do with background. Pretty much we need to, first of all, create a couple of files, SpikeField header file and SpikeField C file. Okay, in header, the same thing applies, pragma once, type def struct SpikeField, so that we don't expose internals of our struct. And yeah, just introduce our custom type. Then SpikeField load SpikeField, same as background. What was there? Draw SpikeField. And unload SpikeField. We can copy those method declarations, jump to C file, include Raylib, include our header file, and start working on these things. Now, SpikeField struct. For background, we really didn't need anything. We just used the 2D shader, relying on built-in draw rectangle, which gives us necessary vertices, and all the fragments were supplied to us into our fragment shader. For SpikeField, we would need to construct a mesh, right, that builds our spike. This will be a very, how to say it, simple spike, in a sense that it won't be like a pointy thing. For our use case, I'll show you how we can simulate a spike in a sense. Yeah, we will construct all the vertices ourselves. We will then try to draw a mesh, draw a single spike, see how it looks like, how we can manipulate it, and then we will reuse it by using OpenGL's instant drawing. So we will say how many instances of the same mesh we would like to draw. Each mesh will get its own transformation matrix so that we can actually move it around the scene and build a full field of the same mesh. Alright, so first things first, SpikeField. We again use memory allocation provided by Raylib. We need to also free it in the end. And here we'll need to build spike mesh. All right, let me think whether we need to jump right into it or we need to draw a spike. So how are we going to draw it? Pretty much we will initially, as I said, we want to draw a single spike. So it will be draw mesh call. We have our mesh, then it wants some material, so we'll need to introduce that as well. And then there's going to be some matrix. For matrices we need remath. We can say that hey, my matrix is going to be identity, so it won't apply any changes at all. We need some material, which will be default in the beginning. So material is build spike material, right? And as we want to draw the field, as you saw in the beginning, under some angle, we would like to draw it with our custom camera. So it was, I don't know, like mode 3D, right? With some camera of our own and mode 3D. We will define camera soon as well. Or maybe we can even start with camera. Let's see. Const camera. Let's see. The camera has type 3D, has a few fields in it, which we want to populate. Let's start with projection. Yeah, it's going to be perspective projection, not orthographic. Field of view, I think 45 is fine for our project. Up vector, we are pretty much using the usual x0, y is our up, z is 0. Our target, where we're going to be looking at, is going to be x0, y0, and z0. So we're going to be looking at the center of our world. And camera position, this is something you can play with. I will try to define some values that I came up with earlier, something like this. If not, we will try to adjust them as we go. I think something like this works. So this is the camera that we're going to use. It will be used in this DrawMesh so that some matrices like model view projection matrix is calculated by us based on this camera by Raylib. It's provided to our shader right away. We don't need to do absolutely anything. All right, so now that's set, we can actually start working on our mesh. All right, so first of all, let me something like online drawing board, maybe the sketchpad. I don't know, like what here works. I need a simple, yeah, why doesn't have white background now to draw. All right, so really what I want to do is I want to have a spike which is going to be two flat squares which are like crisscrossed together. So we will have one square, right, and there will be another square like this, and they are like crossing right here, right? So this doesn't look like a spike, but for many use cases some simple mesh, simple as this one, will work, because we will reduce these sizes. The height will be much bigger than the sides, therefore we will end up with something very narrow in a sense like this, and then there's another spike going something like this, with the middle being right here, right? And as this thing, oh my god, as this thing gets really small, you won't even notice like how that spike is drawn. But what you need to understand is that we're simply using two squares, and then each square is actually combined of two triangles. So like one triangle, second triangle, and same goes for that spike. One triangle, yeah, I think I misdrew that. One triangle, four triangles. Right, so we can start defining some constants here. So for example, we can define that our spike mesh triangle count is 4. Right, so as you saw, we pretty much need 4 triangles to draw the whole spike. Then we can define vertex count. Each triangle has 3 vertices, so we can say triangle count times 3. Due to const expression, it calculates it, says it's 12. Then we can actually define our vertices. So spike, it's float, spike mesh vertices of some length, and the length is going to be vertex count times 3. So we have 12 vertices, and each of them is composed of 3 elements, x, y, and z. That's why it's the vertex count times 3. First of all, let me fill it in with empty things like this. 2 and 4. right? So if we look at one square, we're looking at this square. This is the middle. This is where we will have another square crossing it. So this one is pretty much 0, 0, 0. This particular point, right? So that's the center of our world. That's where our camera is looking at. So you can understand that this one is going to be some minus half width. This is going to be plus half width, and this is going to be height. And because these are like local coordinates, we can say that this is going to be minus half. This is going to be half. And this is going to be 1. Right. And in order to define vertices, right, if we look at this one, this is minus half, 0, 0. Then we go to this point. From here, yeah, to this point. So half, 0, 0. So it goes from this point here, then here. Oh man. Where we define this point, which is minus half, y is y, 1, and z always stays 0. Then we define second triangle, and then for another square as well. So let's think about it. First of all, minus half, 0, 0. That's the first point of the first triangle. Then we go to the right, we end up at our half, 0, 0. And then we go to the left, which is minus with y being 1. So this is this triangle. This point, minus half, 0, 0. This point, half, 0, 0. And then we're going up and to the left. So minus half and 1. Boom. Second triangle, it can actually start from this point. So it starts from here. It can then jump to this point, which we had, half, 0, 0, and go up here, which is half, 1, 0. And for the other two, it's actually quite easy. We can copy the y values, 0, 0, 1, 1, 0, 1, and just carry over the x's into the z values. Minus, minus, for here it's minus 0, 5, 0, 5, 0, 5. Well, hopefully I didn't make any mistakes, but I don't want to waste too much time. You can check these things on your own. Now, why did we add all these things? Well, because we want to define our mesh. We want to construct it by hand. Let's do that. Mesh build spike mesh. So we can have it initialized with everything to default. All the pointers are nulls, all the ints are zeros. Let's copy over, so all the fields. And really, we don't have anything animation related, no animation vertices, bones, whatever. Identifiers will be set up later on by Raylib itself. We don't use any of these things, but we do use these three things. So one of the reasons I defined the constants above is actually I knew that we need to define these fields for our custom mesh. So mesh vertex count is something that we already defined. Mesh triangle count, we also defined it. Now vertices is an array that we also have here, but first we need to actually allocate enough space for that. So that's as easy as our vertices, right? So it knows the size of the whole array that we defined there, it allocates enough memory, and then we can just copy. And first is destination, so we copy into mesh vertices. Source is our mesh vertices, spike mesh vertices. And how much data are we copying? Again, this is already known to compiler. Once that's done, once mesh is set up, we can actually upload mesh, and it uses the field dynamic. I think it signifies how often this mesh is going to change, and because our spike mesh never changes, we can set false here. Right, so what it does is upload mesh vertex data into GPU, provide VO, IDs, and this is pretty much it. We've built a spike mesh. Now we can actually draw it, but to do that we need some material. Let's quickly define build spike material method. I think it's the load material default, and we can return that. So really material is some shader, some maps, some params. It is required to draw the mesh. So we haven't defined any shader, so it has put something default that it uses. Let's see whether we can see anything on our screen. We don't, and most likely just because we haven't actually updated our main. First we need to load the SpikeField. Then we need to draw our SpikeField. And we need to unload SpikeField. So before I jump into trying to run it, we need to update this unload SpikeField, where we need to unload probably mesh, right? So field mesh, and we need to unload material, which is field material. Back to main. This should be it. Let's see what we see on our screen, if anything. All right. So now we see one of our squares and we don't see the other one. And the thing is that by default, Raylib has backface culling turned on. So depending on where our camera is, at which direction we're looking from to, right, it can actually believe that it needs to hide some triangles. So triangles are defined in counterclockwise direction, its vertices, its positions, and based on that, OpenGL can detect whether the triangle is facing us or facing away, and it decides not to draw the triangles that are facing away. In our case, for this tiny spike, we want it to always be drawn. To do that, we need to disable the backface culling. To achieve that, we need to include, I think it was RLGL, yeah, and there is a nice method, disable backface culling. We're disabling it only for this single DrawMesh call, and then we're enabling it back. If we run our program again, now we can see that we're drawing something, but there is an issue with our triangle, right? So I definitely made some mistake. All right, so this is seems to be correct. Minus seems to be fine, and here on the zeros, 101 minus 0555. Okay. Somehow it is not correct. Let me think. So this is 1 and minus, then we go to 0. There. Seems to be fine. This one is minus. No, of course. Why is it like 0, 0, 0? What the hell? This should be like this. Yep, so just made a small mistake, and this is our spike. Well, it definitely doesn't look like spike right now, but this is how our mesh looks like, which is going to represent the spike. So right now it's quite big, and what we can do is I can show you how we can manipulate it a bit. So instead of providing here, it asks for transform matrix, which we say this is identity, it doesn't change anything. We can say let's do matrix scale. So we can scale our site. So y, the height remains the same, we set it to 1. X we can set to 0.1, and same for z. Right, so we scale these sides, and now the spikes, or single spike, has very narrow sides, but the height is the same. Now imagine we scale it down even further so that we look at it from further behind. The spike becomes much smaller than it is, and you will actually not be able to notice too much about it, like how it's constructed, that there's this just two plain rectangles crossing each other. And that is exactly what we want to do next. So we want to replace a single DrawMesh call by another call which is called DrawMeshInstanced, which says reuse the same mesh with the same material, and tell me how many instances of this mesh you want to draw. So let's say we tell it like 1,000,000 here, it will draw 1,000,000 instances of the same mesh using the same shader. And for each of this instance, it will have its own transformation matrix. And this particular argument, matrix transforms, which applies a specific transformation matrix for specific mesh. So if we say that we have 1,000,000 instances, then we will need to have 1,000,000 transformation matrices defined, because each of its instances is going to get its own transformation matrix. And if you think about it, we want to draw a field, meaning that we want to move those meshes around. They can be the same, they can be of the same height, width, but we want initially to at least manipulate their positions, and we want to build some sort of grid. All right, so to do that, we need to actually update our field, SpikeField, and add those two things. So first of all, this is going to be transforms, so some array of transformation matrices based on our instances count. So how many instances do we want to draw? So let's think about it. Let's say I want my grid size to be something like 128. So something like we end up this many spikes, right? And the field is going to be like square 128 by 128 spikes, which means that it actually represents the instance count. So instance count is our grid size times grid size, right? So we can tell you 16K. But the thing is, as you saw, our spike is currently huge, quite big, and we want to reduce it, shrink it, and I want to define the world space units into which we're gonna put this whole grid. So let me show you. Like, first of all, we defined grid world size, which is going to be in like world units, 2.f, which means like 2 by 2, 2 by 2 SpikeField in world units, right? So this unit is like what you define yourself. And then because the world width, or like this grid in world size, has a width of 2, right? And then how many spikes end up being in a single row? 128, but their width is now dependent on this grid world size. So we can say that our spike width is going to be this grid world size divided by grid size. So each spike needs to be of this particular width, which is 0.0156, to actually fit into the grid world size of 2. Now let's start using all these variables we have just introduced. Where do we do that? First of all, we need to say that our transforms is going to be build spike transforms, and our instances is instance count. Let's define the method static matrix build spike transforms. Now, transforms is really it requires some memory, so size of single matrix times instance count, and so that's how much data we need. We can return this transforms. Currently it's only memory allocated, so there's trash data in there. So what we need to do is we need to go and for each of the spikes define its transformation matrix. Let's see. As we want to place these spikes into a grid, we would like to know what its row is, which is index divided by grid size, and its column, which is remainder of division by grid size. Right? So that's where the spike should end up. Then we will define some x and some z, and finally we can say that transformation matrix for this particular spike instance is going to be matrix, I think it was translate x, y is 0, right? We don't move y at all, so it doesn't get affected, and some z. So x and z, they are responsible, because y is up, right? X and z is responsible for the plane where our grid is located at. So our middle of the grid is going to be 0, 0, 0, meaning that the beginning, the x of first spike, should be minus grid world size divided by 2. Right? Because the last one is going to be half of world size into the positive. Then we need to skip the spikes that are to the left of us, meaning we can multiply a row by spike width. Right? So if row is 0, it means there are 0 spikes to the left. If row is 3, it means there are 3 spikes to the left, because row starts with 0, 0, 1, 2, 3. So if my row index is 3, it means there are spikes with indices 0, 1, and 2 before me. So we skip that amount of width. So, and finally, our center should be half of our width. That's why we add half of our width. That's where our X is at. Really, same is applied to Z, except that we use column here. Absolutely the same logic. All right. Now if we run it, we don't see anything. And we don't see anything. First of all, we don't want this DrawMesh anymore. And we still don't see anything. And if I remember correctly, that is something to do how this DrawMesh instance works behind the scenes and what Raylib does to make it work. So if we jump to raylib.com and we go to wiki FAQ, there's a nice question here. Why does DrawMesh instance not draw anything? And it actually explains to you how with DrawMesh instance there is this transformation matrix that is now no longer uniform. It's actually passed in as attribute, so we need to define it ourselves. So for C example, we don't need shader code. What we're interested in is this. If we have some shader, then we need to apply instance transform. So there should be an attribute named instance transform, right? And we need to apply it to this particular shader location so that it knows how to use it. Now, interestingly, we actually haven't loaded any shaders yet, right? We're using the default material. Let's try with this. For example, this is, I think, material shader logs and material. So this is the default shader that Raylib provides. I'm not entirely sure whether it's going to work or not, but let's see. No, it doesn't. So let's define our own shader, because anyway we would need to do that. So shader for our spike is load shader. Now we have vertex shader as well. Assets shaders SpikeField vs for vertex shader, and assets shaders SpikeField fs for fragment shader. Now we can tell that shader logs with this matrix uniform model, right? So for model, we need instance transform to be set as that. And then we need to substitute the shader, the default one, with our own. All right, so let's jump into our shaders folder, create SpikeField vs and SpikeField fs. Again, set file type GLSL, version 330, void main. So this is our vertex shader, which means we have uniform at for MVP. Then we have, I think, attributes vec3 vertex position, and we have in, what was it, mat for, how was it called? Let me see, SpikeField C. That's called instance transform. Instance transform. Right, so Raylib knows how to provide all of these things. We just helped it with this particular matrix. This needs to be done in this instance DrawMesh call. And in our main, we can say that GL, what was it, position, right, it's going to be MVP times instance transform times vec4 vertex position. Right, so the usual. Usually you get the model view projection based on your camera. Raylib calculates that, but then there is also instance transform that we need to apply before we apply the MVP. So that's where that's how we are able to distribute our spikes into the grid. And then in our fragment shader, I set GLSL file type, void main. Let's see, we need to set the out color frag color. It's going to be vec4 color and alpha 10 and color. Which one do we use? Let's use something like blue maybe, as we haven't used that yet. All right, moment of truth. If we run it, bam, we do see something, but it's actually, it doesn't look like a grid, although it resembles it a bit. And the thing is that we are drawing our, let's say, if we change the grid size temporarily to 8, right, we are drawing our spikes with their like full width of our squares. But as I showed you, in order to have our spikes look like a spike, we need to update the width both for X and Z. And we can do that when we construct the transformation matrix. So not only do we need to translate, we need to multiply two matrices here. Right, so we need to multiply the scale matrix and the translate matrix. So how do we scale? X needs to be not the default one, but as we calculate it in world units, it needs to be spike width. Y doesn't get scaled, the height of our spike doesn't get scaled, so we keep it at 1. And Z, again, needs to be spike width. If we run it, we can now see this nice field. So there are like lots of spikes. We can actually set Y to something like 0.3, so scale it as well. And our field is much lower. So each spike is of lesser height. Unfortunately, like with no lighting, with nothing, this is looks like a box of some kind. But luckily for us, we have managed to draw lots of instances, so 16,000 of them, using a single mesh, single spike mesh, using the instance DrawMeshInstanced call. Now we can proceed with improving this field. So what do we want to do? I want to first of all try and have each spike to have different height. How do we do that? Now, of course, we can do it here in our C code, but it will only... I think it will complicate things in the future. We will either need to rewrite things back into shader, so I think it's best if we jump into our vertex shader and do it right here. All right, so what we want to do is we want to somehow randomize things. Right, so how can we do that? One thing that we have is GL instance ID, right? Because we're using the instance draw call, each of our meshes being drawn, each of its vertices has instance ID. So vertices which belong to mesh instance number 1 have instance ID 1, with 0 it's 0, with 100 it's 100, and so on. So we can say that, let's say, unsigned integer instance seed is, we convert it to unsigned integer plus 1, so that it starts at 1. And now we need to somehow use this seed, which is different for every spike, to generate some random values. Of course, they're going to be pseudo random, and one of the ways we can do that is we can look into integer hashing. And yeah, let me find some nice resource. I think this one. This shows you some interesting 4-byte integer hashing. So that's exactly what we have in GLSL. uint stands for unsigned int. It's actually 32-bit, so 4-byte long. It has like few variations. They all do the same. They have like some different thingies applied to them, and I think the easiest one to port to GLSL is this one, right? It only has some bit magic and that's it. So if we paste it here and say that this is uint named hash, it takes a as param, uint, does some magic and returns it. Now we can do what? Now we can say that how about we have another helper function instead of the one returning unsigned int. We can say that how about you return me a float, and we call it hash01, meaning that our return value is going to be in the range from 0 to 1. If we have some seed given to us, we can say that, hey, how about you calculate some sort of hash given the seed and divide it by, let's say, 32-bit int max. Yeah, this value. Remove the commas. So that way, this hash giving some seed will generate a value from 0 up to this one, and by dividing it by the max value, we end up in a range from 0 to 1, never exceeding it, never going below 0, never going more than 1. And now, interestingly, we can also have something like random range helper function, which, like, if you give me some seed and you can give me a minimum value for the range and maximum value for the range, we can actually use our linear interpolation mix, saying that please start with minimum, end with maximum, and based on the hash1 from the seed, we will retrieve a value from this range, from minimum up to maximum. Now, what does this allow us to do? This allows us to This allows us to generate random height per spike, right? So we can say that how about spike height is going to be some random range. We can use instance seed times some prime, for example 13. Minimum is, I don't know, like something in this range. So we are going to be multiplying our seed by some prime in every invocation of random range or hash, where all the primes are different, so that we end up generating different hashes, therefore being more pseudo-random. Now we have generated some sort of spike height, and now we need to apply it. How do we apply it? Well, we need to first copy local position, it's vertex position, right? So the incoming attributes, as vertex position is, it's defined right here, they cannot be changed, but we would like to say that, hey, local position y, let's multiply it by spike height, right? So we're actually applying this spike height which we generated to our height. Let's see whether that does anything. Okay, it failed, missing return for function random range. Yeah, of course we need to return it. Now it doesn't seem to be working, or maybe we just don't see anything, right? If we run it again, it's really hard to tell because everything's like blue. So let's jump into the fragment shader, and instead of giving a single color, we'll start applying some gradients based on the height. So let's say we say that vertex shader is going to provide us with our spike height, right? And then the color is going to be not some static, but we'll call a method height color given our spike height. Yeah, so it's going to be vec3 height color given what? Given some height. Okay, so let's try and define some colors that we're going to use. vec3 some color, vec3 0, something like this. Let's say we're gonna start with deep purple, then something like magenta, something like red orange, and pale yellow. So these are the colors. Let me try and define them. I have them written down somewhere, something like this. Magenta, Alright, so we have these colors. Now we will have our gradient height minimum defined as something like this, max something like this. Then what do? We can say that t is what? Height minus the min divided by the whole range, which is max minus min. And we need to clamp it 0 and 1. Right, so we want to see where we end up on this whole range of the gradient. So we kind of expect that no spikes are going to be higher than 0.60. So we want to redo the range from this 0.5 to 0.05 to 0.6. Let's see. So if let's define another something like gradient stop magenta, right, something like 36, and gradient stop red orange, something like this. Right, so at 0 we have deep purple, which then gradually goes to magenta, which is at its fullest at this 0.5 to 0.05 to 0.6. Let's see. So if let's say we have our gradient height minimum defined as something like this, then what do? We can say that t is what? Height minus the min divided by the whole range, which is max minus min. And we need to clamp it 0 and 1. Right, so we have these colors. Now we will have our 0.36, then it goes towards red orange, which is at its fullest at 0.68, and then as the spike height grows higher and higher, it will actually reach pale yellow. So we have this float T. We need to check it if it's actually in our lowest part. If it's in our lowest part, what do? We need to return our mix, so linear interpolation between deep purple and magenta, given T divided by gradient stop magenta, right? So this is like our first 0.36, and T is less than that. And we would like to know in percentage value from 0 to 1, how far are we in between deep purple and magenta. Next, we didn't reach or go inside this if, meaning T is higher than gradient stop magenta. So we need to check next checkpoint if T is less than gradient stop red orange, right? We need to return some mix based on magenta, red, orange, and here we cannot use T because T is now, it actually touches the first range of deep purple and magenta, and we need to drop it. So we'll have some sort of local T here, which we need to define something like this. So T minus gradient stop magenta divided by gradient stop red orange minus gradient stop magenta. Right, so this is our second range, color from magenta to red orange, and this is how far we are into that range. And finally, we need to return a mix between red orange and our pale yellow based on, once again, we cannot use T, we have to use local T, which is going to be T minus gradient red orange divided by, and now our final stop is like 1.0 minus stop red orange. Right, so this is the math that shows you how to calculate the percentage of inside specific segment of our gradient range. So there are 3 segments. First one from deep purple to magenta, then from magenta to red orange, and from red orange to pale yellow. And based on the height that we have for our spike, we need to calculate where exactly percentage-wise we are in specific segment. That's why we first need to subtract, right, the previous checkpoint. This gives us how much into the segment we are currently in, and then the whole length of particular segment. Let's see whether it helps us. No, it doesn't. I think yeah, it tells us that our vertex shader is actually not writing anything. So fragment shader is expecting the spike height, but we have the spike height as local value. We don't tell it that this is going to be this. And the thing is that we can say that spike height, or maybe let's do float height, or even random height, then height. And yeah, because y is again interpolated between different vertices, and we multiply it by random height, we can then say that spike height is actually what ends up in our position. Now we see some field, and unfortunately it doesn't look like very much random to me. Minimum, maximum, maybe I made some mistake somewhere. Let me try to understand it. So we have an instance seed. Yeah, we have random height. Maybe that's because in SpikeField C, when we built matrix transform, we're actually scaling this, but we want it to be 1, right? So it was actually applying 2 transformations for the height. I put here 0.3 to demonstrate how we can manipulate our height from C code when we build transformation matrix, but now we're doing all the transformation inside the shader, and no, it didn't really help for some reason. All right, let's try to understand. Something's not right in our vertex shader. We receive everything, we receive local position. Of course, we calculate local position, right? We get the spike height from it, but in our final position, we still use vertex position, which is unchanged, as I said. So we need to actually supply local position right here. And now this seems to be more like a randomized field, right? So each spike gets its own random height. We use its instance ID, then supply to some hashing. Every single one has its own unique seed value. We hash it, so we get another unsigned int in return. Then we transform it into 0 to 1 and use it in linear interpolation to pick a value in range from minimum to maximum. So that's awesome. So next thing on our menu is the pi symbol itself, right? So if I quit it, and I think I have it somewhere in my downloads, mask png, I can copy it to assets. Let me open it to show you. Found it somewhere on the internet. So this is pi. Everything outside of pi is actually transparent. So alpha is 0, while the pi itself, I think, is opaque. So its alpha is 1.0. All right, so now we can update our SpikeField. I think it's the material that we're interested in. We should not only load the shader, we should also load the texture, which is going to be called, let's say, mask. Load texture, assets, mask png. Next, we should set some texture filter for our mask, which is going to be bilinear. I'm not entirely sure like how anything of this will help us. So just linear filtering, some interpolation happening here and there based on the size, the scaling of the mask. But then we need to somehow apply it to our material. So there should be some texture material or material texture material set material texture, right? So we have our material. Then there is some map type. Texture is mask. What is map? It should be, I think, material map. I think it was diffuse, no? Material map. Yeah, it should be diffuse. So it's albedo, it's right here. And the thing is, when we set the material texture to this particular location, right, map index, it will end up in our shader. If we jump into vertex shader, set file type GLSL, because I closed the editor, it lost it. Now we have a uniform, again supplied by Raylib itself based on what we just did. It's going to be sampler 2D texture 0. So the naming is very important. So it's actually looking for this name in the shader, and if it finds one, it will actually map it based on what we set here. So we loaded the mask, and now it ends up in our texture 0. So really what we're interested in is we need to look at this mask and check whether our current coordinates end up with alpha 0 or alpha 1 in the mask. So if it's alpha 0, meaning it's a transparent background, meaning it's not pi symbol, so the height can be this low one. But if the alpha is 1 or near it, we can generate much higher spike so that the pi symbol becomes distinguishable. So let's try and do that. First of all, let's maybe try to extract some things. So float, let's call this thing ground, height min, just for reading, so that, easier to understand later on what this constant mean. Ground height min, ground height max. Then we ground height, rename it, just not to forget later on to do that. Yeah, let's keep this one. Then we introduce something like pi height min, something like 40 maybe. Then max, something like this. So if you remember in our fragment shader, GLSL, we're saying that we're restricting the height by 0.60. So let's probably not have super bright yellow at the top and limit the pi height by 55. Which means that we need to also generate pi height, which is going to be random range with some instance seed times 17, pi height min, pi height max. Right, so we now have two heights, and we need to pick one based on the texture. How do we do that? We can say that mask alpha, let's sample our texture, and here we need to define vec2 xy, because it's a sampler 2D, it's a 2D image. Which pixel do we want to sample inside our texture? So really we need to have something like grid UV. So where are we in our grid for this particular vertex? Let me think about it. Okay. So what we need to know is where are we in the row, which row we have, which column we have in the grid. And really this is what this is: instance ID divided by grid size, instance ID remainder of division by grid size, so same as we did in our C code. And then vec2 grid UV is nothing but float from row, float from column, divided by what is divided by grid size -1. So if we somehow, so all right, so again the grid size is something that we set 128, This allows us to understand in which row our current spike is, in which column it is. So the grid UV is actually normalizing it to 0, 1. And because row is from 0 up to grid size but not including, that's why the -1 is here. Right? Because the largest row value is grid size -1 divided by grid size -1 ends up being exactly 1. So what we're missing is this grid size. So we need to actually ask it. Grid, it was end, right? Grid size. Let's quickly jump to our SpikeField C. And this can be done right here in our spike material. We can probably do it this way. We have grid size available to us. So in our build spike material, we can set shader value. So that's for our uniforms. To our shader location index, we can get shader location. Again, same shader. Name was grid size. What kind of value do we want to set? Well, it was grid size. And uniform type is shader uniform int. Right? Because it doesn't change, we can set it only once, and we don't need to have any like sort of update method, update spike field. This is like one-time thing. Grid size never changes. We grab in place the grid size location of our uniform from the shader and set the value to grid size, which is 128. Let's jump back to our vertex shader. Now that grid size is available, we can now grab the alpha, but this is actually RGBA texture, the sample, so we only need alpha from it. That's why it's float now. And then we can say that pi mask is what? It's probably something like smooth step between 0.4, 0.6 and mask alpha. So let me explain what I did here. Now, because we have texture where pretty much the alphas are 0 and 1s, but at the edges, depending on like filtering, we might have some alpha in between 0 and 1. And we're saying that any alpha value less than 0.4 gives us pi mask as 0. Any value greater than 0.6 will give us the value of 1. So we're pretty much sure that this is pi. But in between these values, from 0.4 to 0.6, we are interpolating between 0 and 1. So that the pi edges can actually have like higher height than our ground, but lesser height than our pi itself. Now finally, we need to tell that random height is a mix starting from ground height up to pi height based on our mask value. So if mask is 0, we pick the ground height. If mask is 1, we pick the pi height, which is much higher, and in between we just mix, meaning that we pick some height in between, linearly interpolating it. Then our random height remains the same. Let's see whether like it works or not. And well, it worked. Really, like no mistakes there. Now I can definitely tell you that it's a bit more chubby than the initial result that I showed you, and we can fix that by jumping into our SpikeField, and instead of using grid size of 128. Let's increase it by 256. Right, so it's much more spikes in our grid. We run it again, and it looks much more smooth now. So the thing that's missing is our animation. I don't know like whether you can see it in the video, but the background is being animated based on time, but the grid itself currently doesn't do that. So let's fix that. We jump into our SpikeField and we need to add the time location because in our vertex shader we will need our uniform float time. Right, so we want to also receive time from our main and animate some things based on time. All right, so back to SpikeField C, we need to set this time location, which is set where we have it right over here. Field time location is get shader location. Shader we retrieve from material, and it's time. And of course we now need another method saying that void update SpikeField, which gives us time, and then we can set shader value, field material shader, location indexes, field time location, value is our time, uniform is shader, uniform float. Jump in our main, we can say upgrade SpikeField. Okay, we are missing the method declaration in our header, but yeah, let's add it field time. Oops, field time. Now if we jump to Spike header file, it was void update SpikeField. We run it. Okay, no too few arguments. Okay, field. All right, so it compiles, it still runs. Our time is now available. It's available right here through this uniform, and we can now start manipulating these heights using that time. All right. So we kind of want the field to wobble a bit, right? Our SpikeField, both the ground layer and the pi level. So what we can do is we can add a couple of methods like float ground wobble and pi wobble. What we can have here is probably receive some seed. And initially I'll return 1.0 and apply it right here. So once we have our random ground height, we can actually multiply it by ground wobble with instance seed time some different prime. Same applied for pi height, pi wobble, instance seed times, I need more primes, like first primes. Let's say, I think there is some list here. Let me pick 47. So what we are about to do is we want our ground wobble to return some value in range, I don't know, like this is arbitrary, but something like from 0. I don't know, like 85 to 115 or something, right? So then when we multiply it with our initial random range, it will adjust the height, and this interval really depends on time. So it will gradually grow, go back, grow, go back. So that's why we have like 1 initially because it doesn't change when we multiply by it. And what comes next is actually exactly what we did in our background section. So what we want to do is we want to introduce some sort of wave. But now we can work with time. Time times tau, meaning that the sine wave goes its full loop from 0 to 1 to -1 to 0 in 1 second. Let me open up background FS to copy the tau over. Let it be somewhere here. All right, so we have this wave. We want it, let's call it wave A. We want it to have some frequency A. We want to have it, I think, some sort of, I don't think we need phase, but we want to have some amplitude A. Let's see, so frequency A is going to be random range. Again, we need to have our seed times 107 from something like, let me check, 45 to this one. So we get frequency in this range from 0.45 to 0.80. We applied, and then amplitude A is going to be 0.13. Right? Now we can say that, yeah, so maybe do it like this, amplitude A, so that this is actually a wave A and it's multiplied by amplitude A. Let's see what it does. Right now you can see our spikes being animated, but initially when we run, right, you can see that they almost move in the same in the same frequency. That's because we start, or because we start in somewhat like in sync, but we desync it pretty quickly. What I want to do here is probably have another, not probably, but definitely have another wave, which is again times tau times frequency B. And then we have wave B times amplitude B. We're gonna have frequency B, some random range, given seed with some 277, let's say, and it's going to be like a slower one. And this one is a new concept where we add two waves. Okay, yeah, I didn't define amplitude. This is correct, but float amplitude B, I think it's something like this, if I'm not mistaken. If we run it again, there's some 45 random. Why did it go? It's range. Oh my god, it's random range. Mistyped method name. All right. We probably could use some phase, yeah, because phase is the same, they all start with somewhat the same. So let's do this. Phase A is Let's say hash 01 times tau. Hash 01 gonna get some seed times 541, and this one gets phase B. Hash 01 seed times, I don't know, 449, and then our wave can have plus phase A plus phase B. So this one makes sure that every single spike gets a different offset, so that we don't start all with the same phase. Oh my god, again, float, syntax error, which line? 42. 42, yeah, semicolon. Yep, so instantly, just because we have different phase or different offset for each spike, we no longer have that initial wobble of the whole field. But that effect is actually pretty interesting, that we would want something like that applied to our Pi. We'll see how that works. But before we jump into that, I would like to show you this thing, what it does. Now we have two waves and somehow we simply sum them up. If we jump back into our, was it Graphtoy? Right, let me show you something. Like if we have sine of x, which looks like this, we can take another graph, sine of x, but have it at a higher frequency by 3. And then it has, let's say, much lower amplitude by 1. And then maybe, yeah, let's also, yeah, like 30, that's too much, but yeah, maybe it works, right? So it's higher frequency, some lower amplitude, and now we can actually introduce the third one, which is sinus x plus whatever we have here. So we end up with this nice thingy. So this is called wave superposition in, I think, yeah, superposition principle, where we pretty much just add it up, right? So the waves add up. This is exactly what our Graphtoy shows. If we have one sine wave, which is nice and smooth, and then there is this wobbly small wave, and we add up, their values are simply taken from first wave plus the second wave. And this ends up like providing a bit more randomness into the movement of the spikes. Before adding second wave, you could potentially notice some sort of, you know, like smoothness into the movement, but with superposition principle, having this smaller wave, we added, we introduce a bit more randomness to their movement. All right, so now we have the ground moving, and we want to do the same with our Pi. And really what I can do is really just copy it over, rename it to Pi wobble, right? If I run it, well, yeah, Pi is shown, but it doesn't look that great. First of all, the spikes are very high, the Pi is static, and as I said, I want to get that effect where Pi starts to rise and then go down a bit. So let's see how we can achieve that. Well, first of all, let me change the primes. 599, for example. Next one, 191. Next C times 679. Another prime 367. All right. Phase amplitude for pi should be something like 0.11. Second one even super lower. And the thing is, if we run it with like updated values, it changes like a bit, but pi is still pi. And what we want to do, really interestingly enough, is that instead of generating a random frequency for each and single spike, we can set it to the same value. Well, that didn't work. So frequency, amplitude. I think the second one needs to be updated as well. Frequency will be something like 220, 330. Amplitude B, frequency. Yeah. Run it. Kind of moves very slowly. Something's not right over here. Maybe we can, yeah, drop the tau thingy, and what we want to do is we say times some phase. Now this allows our pi to rise and go low. But at the same time, this one isn't doing that great. I think maybe this is the mistake. Yep, looking a bit better. So this is how we achieved like this breathing effect, in a sense, for our pi, is that here, instead of, first of all, instead of using random range, every single spike gets the same frequency, and then the phase is, first of all, doesn't rely on tau, and second of all, it generates the values, like if we say hash is like from 0 to 1, then we move it interval into -half up to half, and then just reduce the values a bit more. So we concentrate around the 0. Here we concentrate on the upcoming values, so more we move it, we shift it into one direction. Here we shift it into two different directions so that they kind of breathe around the same value. All right, so I think there is like one more thing that we want to do. Right now it looks very much what I promised you to deliver in the beginning. But one more thing I wanted to include into this tiny project of ours is how do we pause the animation, right? So for example, for my thumbnail screenshot, I would like to pause the animation at some very nice coloring position, make a screenshot without relying on like timing when the animation is playing. And it turns out that adding it in our case is very, very easy. So what we can do is we can add a boolean, say paused, starts with false. Then time is only updated when it's not paused. right? So right now nothing changes, it continues to work, right? It runs, animation runs, time's always getting updated. But first thing which we can do, we can check is key pressed, something like key space. Then we can switch the post value. And once I press space, right, post is now true, time doesn't get updated, and the animation stops. Even though the shader keeps rendering the same scene, it's just it receives the same time value over and over again and produces the same effect. That's where we see how this pseudo-random generator works, where our hashing returns the same value for the same seed all the time. Yeah, maybe like one more thing is that we can jump into SpikeField, and where we define our camera. Yeah, like here, for example, I could say that if def screenshot, then I use some position, else I use this position, and if. Right, so right now no screenshot is defined, no such variable. We run it, it's all nice, but let's say I say define screenshot, and we change it to some different, I don't know what to use here. Let's say higher, less, let's remain the same, right? We can change the angle a bit, and we can pause if we want to. So space pauses. We find that this angle is really nice. So that's one of the ways you can manipulate your animation and stop it at the right time, and maybe change the camera angle just for that screenshot value. So this was pretty much it, everything I wanted to tell you. Hopefully you liked it. This was quite an experience for me to devise something from scratch without ever seeing anything like that done before. Hope you liked it. If you do, like the video, subscribe to the channel. More stuff is coming. See you. Bye.